Good day. My name is Mironchenko. Welcome to my talk on stability of networks of infinite dimensional systems. We are surrounded by networks, by transportation networks, electrical grids, and social networks. And these networks grow larger and larger from year to year. Emerging technologies like 5G, Internet of Things, or cloud computing make this trend even more distinct. Moreover, the components of these networks may belong to very different system classes. Some of them may be effectively modeled by finite dimensional systems. The others may be delay or partial differential equations. The way how the systems are connected may vary drastically. Some of them may be connected via boundary, while another via domain. Moreover, even the size of the networks may be unknown due to the agents which either enter or leave the system. At the same time, safety and reliability of the networks needs to be analytically verified. This calls for a unified toolbox how to study stability of complex systems with different components. Today, we focus ourselves on one of the important questions in this respect. Under which conditions an interconnection of stable systems is again stable? This talk will be divided into two parts. In the first part, we focus on the simpler case of couplings of two systems, and we use Lyapunov methodology to develop small gain conditions to stability of the networks. In the second part of the talk, we go for a much more general class of infinite networks consisting of heterogeneous components, and we discuss how small gain approach can be used to study stability even of such complex systems. Now let us consider the following class of control systems. These are evolution equations in a Banach space X. A here is a generator of a strongly continuous semigroup which we denote by T. So A is defined on some domain D of A, which is a dense subset in X. We assume that F is Lipschitz continuous with respect to the first argument and continuous with respect to the second one. Also, we assume that the inputs are piecewise continuous functions mapping positive reals into some non-linear space U. Under assumptions which we have imposed, there exists a unique mild solution for this system. And mild solution is a continuous solution of such an integral equation, where x0 is an initial condition and u is a corresponding input. Now I would like to introduce the main stability concept for such systems. To this end, we need two classes of comparison functions. We say that the function is k-infinity function if it is 0 at 0 and increasing to infinity. And it is beta is called a KL function if it is a function of two arguments. With respect to the first one, it is 0 and 0 and increasing, and it decreases to 0 in the second component. Now we can formulate the main property for this talk. We say that the system is input to state stable, or shortly ISS, if the norm of the trajectory can be upper bounded by a sum of two functions, a KL function beta and a k-infinity function gamma. Beta describes the transient behavior of the system, and gamma describes the asymptotic behavior of the system. To understand the essence of input to state stability, consider first the case that u is identically 0. Then this term vanishes and the trajectory of the system is upper bounded by the function beta. As beta decays to 0 when time goes to infinity, then the trajectory decays to 0 as well, which means that every input to state stable system is uniformly globally asymptotically stable. On the other hand, if u is non-zero, then there is no guarantee in general that the system will converge to zero. However, it does converge to the ball with the radius gamma of norm of u, and this for any initial condition. This means that gamma is a kind of asymptotic gain for our system, and ISS implies a nonlinear version of input to output stability for a control system. This feature that ISS unifies internal stability in the sense of Lyapunov as well as input-output stability has made ISS one of the key concepts in modern nonlinear control, which can be used to design nonlinear controllers and observers for nonlinear systems, as well as to study stability of coupled systems. We introduced two more notions. If the ISS estimate is valid only for the zero input, then we call the system uniformly globally asymptotically stable at zero, or shortly zero U gas. If the norm of the trajectory satisfies the estimate where the gamma of norm of u is substituted by such an integral term, where theta and mu are again k-infinity functions, then we call the system integrally input to state stable. So recall that our input space is a space of piecewise continuous functions, and therefore in the input to state stability we had a bound in terms of the maximal magnitude of the input. Here we have a bound in terms of the integral of the input, so basically to some extent a bound in terms of the energy supplied to the system. In particular, for ISS systems, the trajectory cannot be unbounded for our choice of input space, and the trajectories of integral input to state stable systems can be unbounded. In particular, if we take u as a constant input, then we see that trajectory grows to infinity with the time in general. For an overview of the infinite dimensional ISS theory, we refer to these two works, to the book by Yason and Miroslav on ISS of partial differential equations, which concentrates on quantitative aspects of ISS theory, and to this paper by Christophe Brieur and myself, which is devoted to qualitative analysis of ISS systems. Having introduced the ISS property, we need the tools how to study the stability of control systems. Lyapunov functions are extremely important in this respect. We say that a continuous function v is an integral ISS Lyapunov functions if v satisfies such sandwich estimates where psi1 and psi2 are k-infinity functions, and if in addition v satisfies such an inequality called dissipative inequality. V dot here is a derivative of Lyapunov function along the trajectory where x is initial condition and u is an input. So formally it is defined here. What we see here in this inequality, if the state x is large enough with respect to the input u, then this term is negative, and thus Lyapunov function decays along the trajectory. If otherwise u is large enough, then the Lyapunov function may increase up to some point. If in addition to this inequality we have that this decay rate is an unbounded function, then the function v is called ISS Lyapunov function. The basic result is that existence of ISS or integral ISS Lyapunov function implies ISS or integral ISS respectively. Consider the interconnections of two integral ISS systems. The first of them is called sigma 1 and it has state space x1. Here f1 is some nonlinearity. It has two inputs, x2 and u. x2 is called internal input. This is the input from another subsystem. And u is external input. The system sigma 2 has x2 as the state and x1 as internal input. U is again external input. So A1, A2 are again generators of strongly continuous semigroups. We can consider this as a single system and reduce the state space for the whole system, etc. in a natural way. So the question is how to study stability of such coupled systems. We will assume that both subsystems are integral ISS. I mean, clearly, this is a restriction. So in general, a coupled system may be stable even if the components are not. But anyway, for many systems which we deal with in the real world and in engineering, they are internally stable. And then the question is, what will be the behavior of the interconnection? Therefore, from now on, we will always consider that the subsystems are stable in integral ISS sense. Furthermore, we assume that there exist Lyapunov functions for these both subsystems. And we know the decay rates and the influence of the inputs. So now we have this data consisting of alpha i's, of sigma i's, and kappa i's. Now I would like to extract from all this information that which is relevant for stability analysis of the network. And it turns out that the crucial role is played by such compositions, which can be called gains, describing the influence of the one system over another one. For example, the influence of the system sigma 2 on sigma 1 can be described by such a composition. So here this is the generalized inverse of alpha 1. So if alpha 1 is unbounded, then it is just standard inverse. The definition for this generalized inverse is given here. So what is the sense here? The larger is sigma 1, the more is the influence of the second system over the first one. And conversely, the larger is alpha 1, the faster is the system stabilized, and therefore it reduces basically the influence of the second system over the first one. So this makes this natural, these terms. Analogously, we construct this gain, which describes the influence of the system sigma 1 over system sigma 2. And now we have the following result. Assume that both Lyapunov functions are some functions of the norm of the corresponding state. And assume that if we make some arbitrarily small increasing of the gains, so if C is equal 1, then this is our gain, and this is the gain as well. We increase them slightly and take the composition of the gains. Basically, we show what is the loop. I mean, what is the influence of the system more or less on itself. And if this is a contraction, then this means that there are no loops which lead to increase of the state of the system. And then one can show that the interconnection is integrally ISS. If, in addition, both decay rates are k-infinity function, then the interconnection is input to state stable. Moreover, we can even show what is the Lyapunov function for the interconnection. And it is given in this form. So this result is proved in this paper, and it is an extension of the corresponding result for networks of two finite dimensional systems. Next, we would like to apply this result and show how it works in practice. We consider such an interconnection of two reaction diffusion equations. They both have Dirichlet boundary conditions, so 0 on the boundary, and both have some nonlinear terms. So here we have quite strong polynomial nonlinearity, and here again, so polynomial and also rational nonlinearity. Our idea is to analyze under which restrictions on A and B, the whole system will be uniformly globally asymptotically stable. Well, First of all, the question is how to choose the state space for the system, because clearly the question whether the system is stable or not depends on the norms. So we choose the state space for the first subsystem as L2 and for the second subsystem as H10. Our strategy to analyze the stability of the network is first to show the integral ISS of the first subsystem, input to state stability of the second subsystem, and then use small gain result to get conditions for stability of the interconnection. We consider such an integral ISS Lyapunov function for the first subsystem. So as you see, it is some k-infinity function of the norm of x1. We can differentiate v1 and we obtain such a condition. Next, for the second subsystem, we choose the squared norm of the state in H10 as the Lyapunov function. And again, after some computations, which are too long to be presented here, we obtain such inequalities. And we have all the needed information about alpha i's and sigma i's. Now we can formulate the conditions for uniform global asymptotic stability. So the system is, the interconnection is uniformly globally asymptotically stable if the coupled gains slightly increased are contractions. If we substitute all what we have obtained here, then we see that this will be equivalent to the following two conditions: that B must be positive and that this condition must be satisfied. And this gives us sufficient conditions for the stability of the network of two highly nonlinear reaction diffusion equations. Well, let us summarize. If we want to study stability of two coupled systems, we can verify that both of them are integral ISS, compute the corresponding gains, and check the small gain conditions. These results have been shown and also presented on an example for in-domain coupled systems. In many cases, the systems are actually coupled via the boundary. This makes the stability analysis much more complicated. However, the small gain theorem itself can be extended also to this case, as long as the coupled system is well posed, and as long as we can compute then integral ISS Lyapunov functions for subsystems. And this is an essential difficulty because we know quite simple systems for which no coercive ISS Lyapunov functions exist, or at least we don't know whether they exist at all. Therefore, in this case, so-called non-coercive ISS Lyapunov functions can be useful, and probably the small gain theorems have to be extended to these less demanding types of Lyapunov functions. However, this can be a nice topic for another talk. In this talk, we will no more analyze the non-coercive ISS Lyapunov functions. The results which have been presented here have been shown in this paper. So for more details, please consult this one. Now, after we have discussed this one type of small gain result for two systems, I would like to give some literature overview. The first paper where small gain theorems have been showed for couplings of two ISS ODE systems is this paper by Jung, Till, and Perley. It is a milestone in the development of the ISS theory because this is for the first time that the small gain theorems have been used in the context of the state space systems. Before, they have used for a long time within input-output approach. With this paper and with the help of the ISS framework, they entered state space defined systems. Afterwards, this result have been extended in a number of papers. In particular, they these results have been extended to the couplings of arbitrary finite number of input to state stable ODE systems in these two papers, and it was extended also to integral ISS in another papers. The importance of this result led to the development of small-gain theorems to other classes of systems, in particular to time delay systems and to infinite dimensional systems of evolution type, so which we have considered before. In parallel with all this development, there was a considerable effort to study infinite networks, which have so-called spatial invariants. Spatial invariance basically means that all systems are similar to each other and they are connected in a similar way. And however, we have infinite number of such systems, which makes the analysis really challenging. So there is a very large literature on this kind of networks. And basically, these were two lines of development for stability analysis of networks. Very recently, there was a serious effort how to extend the small-gain theory to infinite networks. This would allow us to study nonlinear infinite networks without any spatial invariance assumptions. In particular, in these papers, some results have been proved. Today, in the second part of this talk, I would like to present general nonlinear ISS small-gain theorem for infinite networks. In this result, we will be able to deal with finite and infinite networks. The subsystems may be of any type, so some of them may be ODEs, PDEs, delay systems, etc. And the subsystems can be of any dimension. Moreover, we allow for couplings of any type, so both in-domain and boundary couplings are allowed. And we don't need actually even the assumption of spatial invariance. In order to study the problem in such a general setting, we need sufficiently general definition of a control system. We assume that the control system is given by a triple X, U, and phi, where X is the state space, U is the space of external inputs, and phi is the solution map. We say that this triple is a control system if it is forward complete, so the solutions exist and are unique for any initial condition and any input, and are defined on the whole R+. We assume that each solution is continuous and satisfies the cocycle property. Cocycle property basically means that if we pick any solution and we go along this solution and stop at some point and then reinitialize the system with the current state and current input, then if we compute the new solution, we will go along the previous one. So this is the idea. And basically, these are very, very basic assumptions which are satisfied for many classes of systems. In particular, ODEs, evolution partial differential equations with Lipschitz nonlinearities, which we have discussed in the first part of this talk, as well as broad classes of boundary control systems, time delay systems, are all within this very general class of systems. Now, the question how to interconnect such systems. In the first part of the talk, we had equations which govern the dynamics of subsystems, and therefore it was quite clear what is the input from other subsystems and how we interconnect the systems. Here it is not as clear because each subsystem is defined by the solution map. Anyway, I will not explain the ideas how to do it, but we have adopted the framework developed in this paper for two subsystems, and we extend it to infinite networks. So basically it is presented how we can really interconnect the abstract systems even if we do not have equations for them. I will not go anymore to this formalism and proceed to the stability analysis. We will need one result from the ISS theory. So this is just, we recall what ISS means, that it is this estimate for the trajectory. We need one more property. We say that the system is uniformly globally stable if the trajectory can be upper bounded by a sum of two functions, where the first one depends only on the norm of the state and the second is the standard asymptotic gain. Well, clearly ISS implies this property because beta decreases in time. So if we put instead of time 0, then we get precisely what we have here. So ISS implies this property. Converse clearly doesn't hold. Another property is so-called bounded input uniform asymptotic gain. It tells us that if we start in a bounded ball and apply uniformly bounded inputs, then there is time uniform for all such x and such u, so that for times after this time tau, our trajectory is upper bounded by some epsilon plus gamma of norm of u. Well, and this tau depends also on this epsilon. The smaller is epsilon, the larger is tau. Again, it is quite easy to show that ISS implies this property. Conversely, if the system satisfies these two properties, then it is also input-to-state stable. This gives us a powerful criteria for input-to-state stability of infinite-dimensional systems, which can be useful in particular for the small gain analysis of infinite networks. This criterion is a special case of stronger results which have been shown in this paper. To formulate the ISS small gain theorem for infinite networks, we assume that each subsystem is input-to-state stable. More precisely, we say that the system sigma I is ISS in semi-maximum formulation if the norm of the trajectory can be upper bounded by a sum of three terms. Two of them we have already seen. These are the Kl function beta I characterizing the transient behavior and gamma I characterizing the influence of external inputs. However, now we have also inputs from other subsystems, and so we have further gains, gamma ij characterizing the influence of the subsystem sigma j over the system sigma I. Here we assume that the total influence of all subsystems is a supremum of individual influences. Therefore, we call this semi-maximum formulation. For other application, sum would be here better than supremum. Then this would be summation formulation. We can show small gain theorems for both cases, but here we stick to this semi-maximum formulation to make the things a bit simpler. Now we can define the state space for the overall network, which is the Cartesian product of individual subspaces of the state spaces of subsystems. The norm in the state space is defined as the supremum norm. Analogously, we can define the space of internal inputs. So now, what information do we have about subsystems? We have these transient behaviors beta i's, internal gains, gamma ij, and external gains. Now I would like to impose the conditions on all these functions, which will guarantee that the overall network will be ISS. As we know from the analysis for two systems, which we have performed in the first part of this talk, the internal gains gamma ij play a crucial role for this. Therefore, we take all of them and we combine them into the infinite gain matrix, gamma. This matrix induces, in turn, the gain operator, this gamma max, which is defined in this way. So we have supremum here because we have suprema here. If we would have sums here, then we would construct the operator with sums. So note that this is a nonlinear operator in general, which acts in an infinite dimensional space L infinity plus. So this is a space of all infinite sequences which are uniformly bounded and have non-negative entries. And now the question, which properties of this nonlinear monotone operator ensure input-to-state stability of the network? we need one more property. We say that a nonlinear operator A has the monotone limit property if there is a k-infinity function xi such that any monotone solution for this system induced by an operator A, each such a monotone solution which lives in the positive cone approaches the ball with the radius xi of norm of u, at least at some time. Afterwards it may diverge, but at some time it should come arbitrarily close. Now, with this definition, we can formulate the nonlinear ISS small gain theorem for infinite networks. Assume that we have an infinite number of infinite dimensional systems, which can be of quite arbitrary nature. Assume that all of them are input or state stable, and assume that the interconnection is well defined. Furthermore, assume that the transient behavior of all subsystems can be uniformly upper bounded by a Keil function. And also that we have a uniform bound for all external gains. This requirement is necessary because if it is violated, then even if all internal gains are zero, we cannot in general hope for ISS of a network. So if all this holds, and if in addition the gain operator has monotone limit property, then the interconnection is input or state stable. The proof of this result consists of 3 steps. First, we show uniform global stability of the overall system. Then we show uniform asymptotic gain property, which is the hardest technical part of the proof. And finally, we apply the criterion which we have seen before, that a combination of these 2 properties is equivalent to ISS. This result was inspired by the small gain theorem for finite networks of ODE systems, which was shown in this paper by Dashkovsky-Rufebert. However, for ODEs, which are sufficiently regular, as was assumed here, one can use powerful characterizations of input or state stability in terms of non-uniform asymptotic gain property, which were shown here. This simplifies greatly the proof of the ISS small gain theorem. However, these characterizations hold only for ODEs and only if we assume sufficient regularity. For infinite dimensional systems, they do not hold even for linear ones. Therefore, we have to develop new techniques for the proof of this result, even if we have finitely many infinite dimensional systems. For infinite networks, we in addition had to impose some stronger restriction on the gain operator. So, with the help of this theorem, we can formulate the small gain approach for stability analysis of networks. First, we need to verify the input or state stability of all subsystems and compute the internal gains. Afterwards, we need to verify that the whole network is well posed and construct the gain operator. Then, if this operator has monotone limit property, then the network is input or state stable. This is quite a clear strategy. However, verification of this monotone limit property is in general a hard task. Just note that this operator is a nonlinear operator, still infinite dimensional, and we need to show some property of this discrete time system, which is even a bit non-conventional because we do not have equality here, but just less or equal. Therefore, it is highly desired to obtain some simpler criteria for important special cases. This is what we are going to do next. The first case is a case of linear systems. For the small gain theorem, we need to consider only the case when x is L infinity. However, this result we can show for arbitrary ordered Banach spaces with generating normal and closed cones. So, our result is that monotone limit property for a bounded positive operator A is equivalent to input to state stability of such a discrete time system, which is equivalent in turn to condition that the spectral radius of A is less than 1. And this is equivalent to another uniform small gain condition. So what does it give to us, this result? Now we can formulate the small gain theorem for the linear gain operators. If the spectral radius of this linear gain operator is less than 1, then the whole interconnection is ISS. So we have an efficient way how to check this monotone limit property. You can think also differently about this result, because it does not only give us a way to verify this monotone limit property, it gives us also a way how to characterize input to state stability of linear discrete time systems. For example, by means of this uniform small gain condition. The proof of this result is based on the technique of Fréchet filter powers. I also would like also to note that the condition that the spectral radius of the operator is less than 1 is tied already for finite networks. So if we have a finite network with linear gain operator, which has spectral radius greater or equal than 1, then we cannot guarantee in general input to state stability of the network. Let us go to another special case, to a case where gamma ij are nonlinear functions, but we have only finitely many systems. In this case, the monotone limit property for the gain operator is equivalent to this uniform small gain condition, and even equivalent to strong small gain condition. Why this proposition is important? Because this strong small gain condition can be quite easily checked for our gain operator. And also, this is precisely the condition which was used for the proof of the small gain theorem for finitely many ODE systems. Actually, in the proof of the implication that 4 implies condition 3, we use the result by this paper, where the ISS small gain theorem for finitely many ODE systems has been shown. So this strong small gain condition can be efficiently checked by so-called cyclic conditions. And this gives us a powerful way to analyze the finite networks of infinite dimensional systems. Let us specialize our small gain results for finite networks to interconnections of two systems. In this case, the gain operator has such a simple form. As we have shown on the previous slide, a network of finitely many input to state stable systems is ISS if such a strong small gain condition holds. Now, for the case of two systems, if we substitute this gain operator here, then we see that this condition is equivalent to the following one. What does this condition tell us? If we slightly increase both of the gains, so here rho is k-infinity function. In particular, we can take it epsilon times the identity for epsilon arbitrarily small. So really, if we slightly increase both of the gains, and if the composition of these increased gains is less than identity, then the network of two systems is input to state stable. This is precisely the small gain condition which has been used in this paper to analyze ISS of two ODE systems. Therefore, our very general small gain result for infinite networks contains the existing results for finite networks as a special case, even if we specialize it to ODE systems. Now I would like to present two examples. The first example is a spatially invariant linear system. So consider an infinite network of such components. So each component is identical. So the dynamics of xi is same for all i's. This system is well posed if we choose the state space L infinity and the input space L infinity as well. This system is input-to-state stable if and only if a plus b is less than 1. This is what we want to show. First of all, observe that if we substitute 0 as the input, and if we take the vector consisting of 1s as initial conditions, then this will be the solution of this system. In particular, if a plus b is greater or equal than 1, then the solution either stays bounded or diverges exponentially. And in particular, the system is not ISS. Therefore, this condition is necessary for input-to-state stability of this network. Let us show that it is also sufficient. To this end, one can easily verify such an estimate for solutions of ith subsystem. This shows that each subsystem is ISS and A and B are internal gains. We can define the gain operator, which is now linear operator, and we can verify that the norm of this operator can be upper estimated as A plus B, which is less than 1. Hence, the spectral radius is less than 1, and the network is ISS, since this is precisely the small gain condition for linear gain operators. Well, okay, you can say, good, this was just a linear infinite dimensional system, and therefore we could use also other methods, in particular just make a spectral analysis of the operator which stays here. However, with our small gain methods, we can prove something also for nonlinear systems. Consider a spatially invariant nonlinear system of this form. It is again well posed if we choose the state space L infinity and the input space is L infinity. We would like to show that this system is ISS if and only if both A and B are less than 1. Again, the necessity of this condition can be easily shown. Let us show the sufficiency. Let A and B are both less than 1. We can find a uniform beta for all subsystems and two numbers A1 and B1 such that each subsystem satisfies such an estimate. This can be done by using some Lyapunov functions. What we see here, that each subsystem is input-to-state stable with a uniform decay rate beta, with a uniform external gain, and with internal gains A1 and B1. Now we can define the gain operator, which is now nonlinear operator, actually homogeneous one. And gamma has this form. It satisfies such a condition which implies monotone limit property. And now our small gain theorem implies input-to-state stability of the infinite network. Now we come to the conclusions. Our main result, which we wanted to present in the second half of this talk, is the nonlinear ISS small gain theorem for infinite networks. In this result, we interconnect arbitrary infinite number of control systems, which can be of any type and any dimension. Even the restriction that it is countable number is actually not necessary for this result. It was just for simplicity of presentation. Moreover, we can couple the systems both by in-domain or boundary couplings. So it doesn't matter as long as the coupled system is well defined. For this result, we need only very mild requirements on the regularity. And what we also have, that this result is new even for finite networks of time delay systems. So even if we specialize the type of control systems which we couple and study only finite networks, then this result is already new. Moreover, for finite networks of ODEs, it fully recovers the existing results even under less regularity on assumptions. But these are only special cases. So the main importance is that this is valid for infinite networks of arbitrary infinite dimensional systems. We have developed also constructive special cases. So as we have noted, it is not easy to show this property in general for a nonlinear gain operator. However, we can develop much easier to check conditions in case if the gain operator is linear, or in case if we have finitely many systems which we interconnect. Also, I would like to say that although I have presented the result only for so-called semi-maximum formulation of input to state stability property for subsystems, but we are more general. We can tackle also the small gain theorems in terms of so-called summation type. Also, we have further small gain theorems, not only for ISS, but for so-called non-uniform ISS property and for uniform global stability, which have also important applications. Also, we have constructive special cases for compact, sublinear, and homogeneous operators, which again make it easy to check this condition for these special classes of operators. We have concentrated ourselves in the second half of the talk on the small gain theorems in terms of trajectories. So we have not spoken anything about Lyapunov functions. However, since Lyapunov functions is a key technique how to show the ISS of subsystems, therefore it is natural to use this knowledge also for small gain theorems. So it is desired to have also small gain theorems in terms of Lyapunov functions. Currently, there are several results for nonlinear gain operators, which are described here. However, they are not final and they are shown only under quite severe restrictions on the gain operator. However, for the case of linear gain operators, now we have also quite final results. In particular, if we have an infinite network of control systems, each of which is exponentially ISS with a linear gain operator, then if the spectral radius of the gain operator is less than 1, then the network is ISS. So we have a result which corresponds to the result which we have obtained previously for the case of trajectory-based ISS small gain theorem. There are, however, also important differences, because this result is shown if the state space is LP for a finite P, and our result in trajectories was shown for L-infinity space, which basically makes these results complementary to each other. This result can be also applied to time-varying infinite networks, to consensus in infinite agent systems, and to design of distributed observers. These results can be found in these two papers. There are several open problems. The main open problem is how to show nonlinear ISS small gain theorem for infinite networks. So currently it is completely open, and some new ideas are needed to get this result. Also, it would be nice to relate tighter monotone limit property and uniform small gain condition. We have some results which we have not presented here, which go into this direction, but we have no final result. Also, although our results are very general and applicable to boundary couplings, but it is still a question how to verify our axioms, how to show well-posedness of PDX coupled via boundary, and how to show input to state stability with respect to boundary inputs. These are challenging problem, and currently we have no full understanding how, for example, Lyapunov methods can be applied to study these questions. Finally, I would like to say that the results which I have presented in this talk have been shown in these papers, so please consult them for precise results and discussions. At this point, I would like to thank you for attention. Thanks, and please enjoy the workshop.